Hello everyone. So thank you once again for joining me. So I'm starting a new series of video and this is based on system designs and API designs. So in this series, this is the first episode and I'll be talking about caching, talking about CDN, talking about load balancing, talking about databases, API designs and protocol. So moving forward, okay, let's look at what we'll cover. Let's have an agenda. One is system architecture. We take a look of over what we call single server architecture and the scaling, how we can scale that, and I will look into load balancing, the 6 algorithms within load balancing technology, traffic distribution. I'll move to reliability and high availability. We'll talk about consistent hashing, single point of failure and redundancy. Then when I get to this to the API space, I will look into the contract within the design, look at API contract. I will look into REST, GraphQL, and gRPC. Then we look at the principles, design principle like processes and the life cycle, how to manage life cycle of APIs. And then we'll go into the protocol. So it's like 6 things we need to do here. So let's look at the single server architecture. So in a single server architecture, you have your web application, the database and the cache mechanism, all in one server. So if you look at what we have here, you will see that we have a server here, and we have the JavaScript web app, database, and cache, everything within same server. So it's a very simple and easy to set up architecture. But when things get busy, or when connections are coming in, when you have more traffic, when you have more customers, or maybe you have more workload, using this particular setup, then you begin to see some of the drawback of this particular architecture. So then we go to what we call databases and scaling. So the answer to the problem or challenge of single server architecture is when you scale, is scaling. So in scaling, we have databases and we look at how can we scale the infrastructure itself. So now let's look at this. Before we go into scaling as it were, but let me just back up a bit. Scaling is a way of having multiple servers or upon which your workload can be distributed. So for you to do that, in a single server architecture, we have the database, we have the application layer, we have the database layer, we have the caching layer. Now let's look at some of the things you need to know about databases. So database can be divided into 2 categories. One is relational, 2 is non-relational. So in the relational database is mostly called SQL. Non-relational is called NoSQL. Now, I know most of us, we are very familiar with SQL, that is structured query language. Most traditional database has that functionality. What it means is that a SQL database has a structured schema and a table. You have a table, we have a schema that shows that is like the user. The schema is mostly like the user of that database. So within a user's own schema, you can have tables, views, and some other objects. Now, when you talk about schema now, within your schema, you have tables. Then how does it shape? So it's more structured. It's a structured table, structured schema. Then, but when it comes to non-relational, it's flexible, it's schemaless. Then the other one is ACID. This is that shows that an ACID transaction means that there must be accountability, there must be consistency, there must be isolation, in your database. That shows that if you update your database, maybe from let me say from Ottawa, and you go, maybe you have a connection, maybe in Toronto, you update it again. The transaction you did in Ottawa should reflect as the same in Toronto. So if you are maybe working, around the globe. So the other thing, but in the case of non-relational, is horizontal, like scaling built in. So why ACID is more or less like okay, let's do this. So complex joins. In the case of relational databases, you can do a complex join. That's so you can join multiple tables together, and you can query them as if you are querying from a single table. But in the case of non-relational database, you have document key value graph. So it could be document, it could be key value. So it's more or less like a flat database. Strong consistency, eventual consistency option. So that shows that like I said, you can be sure in relational that when you make a transaction here, it's kind of consistent across every location and everywhere you are accessing it from. So best for financial system ARP, and for non-relational is best for high volume unstructured data. For instance, if you are getting data from social media, like maybe you want to kind of farm in those click, those posts, those video, those like, those things. If you want to have anything to do with those things, unstructured, data like that could benefit from no relational database. So let's look at scaling strategies now. So when you look at scaling strategies here, we have vertical scaling and we have horizontal scaling. Now, when you talk about vertical scaling, you have a server. Maybe you started up with 16 GB RAM, and you have maybe like 1000 SSD of storage. When in case of vertical, what you are doing is that you are scaling it up. You are adding more RAMs. Maybe you are moving it from 16 GB to 24 to 32. You are maybe scaling your storage, your hard disk from 500 GB to 1 terabyte. You still have the same server, just single server, but you're adding resources into it. That's what we call vertical scaling. But when you come to horizontal scaling, that is scale out. It means that you are adding more servers. You might have like maybe 16 GB or 24 GB server, RAM in your server. You might have like 500 GB of storage. But what you are doing is that you are adding multiple servers. You can have server 1, server 2, server 3. So if you look at down here, you will see the client and you have the load balancer. You have 3 servers. This is what we call horizontal scaling. So this by default, most of the time in our environment and in the world we are today, we do more of horizontal scaling. So now we talk about let me talk about load balancing. Now, if you look at the here, you will see load balancing here. Load balancing is like a process of between your server and the client, and what the guy does is to receive that connection from client and kind of point that connection to the right server. Oh, go to server A, or go to server 1, go to server 2, or go to server 3. So here, let's look at what load balancing algorithms. So we have, these are the algorithms for load balancing. We have round robin, cycle through servers sequentially. So that shows that the way that load balancer kind of distribute load and workload is through what we call cycles through servers sequentially. So it takes maybe server 1, then goes to server 2, goes to server 3. Least connection, send to the server with fewest active connection. So when you're using a least connection, algorithm, what you are saying is that, okay, you load balancer, when you want to send connection to the server, look for the one that have the least connection. Let's assume server 1 has a 20, server 2 has a 30, and server 3 has 40. So definitely the next connection will go to server 1, which has the least connection. Then we go to least response time, route to server with lowest latency. So that shows that the algorithm or the load balancer, balance server, will route connection to the server that has the lowest latency. That shows that this is the server that will have least response time. That shows that this server has more resources to respond quicker. Then I have the number 4 here is IP hash. So IP hash uses client IP to pick servers. So sticky session. So it uses the IP address of that server to say, okay, this is the server, this connection should go into or this server. Weighted, route more traffic to higher capacity servers. So here, what it does is to look at the weight of that server, like the RAM, the storage, the GPU, whatever it is, those resources. Look at those ones, the server with the heaviest, the most weight to route to route connection to that. Then geographical route. This time around is like, oh, we have a server maybe for North America, we have another server for Europe, we have another server for Asia, another one for Africa. So what happened is that in this kind of algorithm, what happened is that connection is routed based on your location. That shows that if my connection is instituted or established from North America, then I should be routed to North America server. Is from Africa, I should be routed to Africa server. So then let's look at reliability and high availability. Okay, so consistent hashing. We use a hash ring to find the closest server, minimizes redistribution when node changes. For instance, when we talk about reliability and high availability, now reliability is a concept that ensures that your server is available for connections. And availability is how do you achieve that reliability or redundancy. So it's through a mechanism called high availability. So now consistent hashing is use a hash ring to find the closest server. So what it does is that when you want to make sure that your resources is available, is reliable, it can be, it's accessible all the time. Yes, all the time. Then what you do is to make sure that you have, one of the things you can do is to make sure that you have your server close to client as much as possible. Then instead of you try to redistribute to maybe long distance or what have you, just have something close to that. Now let's look at single point of failure versus redundant design. You can see client gets to server in SPOF and database. You have one server, you have maybe one database, and database even is within the server. So single point of failure, if the server is down, that shows that the service is off. You can't have nobody have access to it. But in the case of redundancy, self-healing, this is not a single point of failure. That shows that you have server A, B, and C. And you can see your database server is replicated across these servers. That shows you have like maybe 3 replicas of your databases. So if a particular one is down or maybe taken out or is not functional or is corrupt, you still have 2 copies of your database. This is a typical example of what we call high availability, we call reliability and redundant design. So it's a best practice for one to choose this redundant design over a single point of failure, like single server architecture. So now I've explained that, so you can see single point of failure. Any component whose failure brings the system down, mitigate with redundancy. I've explained that. So design principle: eliminate SPOF through redundancy at every layer. So a best practice when it comes to design principle is to make sure that your designs doesn't sit at the level of single server. It should be, because single server is single point of failure, it should be redundant, it should be highly available. Now let's go to API design. So I want us to look at the contract, the rest, and some type and what we do here. Okay, so API contract and call styles. If you look at contract define what data is sent. So an API contract is like what data is sent over that API endpoint. Now that's one point. The second point is, how is it structured? Is it structured maybe in JSON format or other format? And what to expect back? So okay, when we send a payload, API payload, what exactly are we expecting the backend system and services to return back to us? So every API style is an implementation of a contract. Yes. So if you look at the client, you look at the API server, you can see the API contract. You know, some making request, response, format, auth, service naming. All these things are things that make up of your contract. So content type, request format, request response structure, all those things, they are part of your contract. Now in API world, we have a lot of API styles, but I think, let me say, okay, we have API styles. So mostly used is REST, GraphQL, and gRPC. gRPC is owned by Google. So REST make use of HTTP and it's stateless. When it's stateless, it means that it embodies, REST API embodies every information that it needs for that session. That's why it doesn't have to rely on maybe historical record or some information somewhere to perform its complete job. So GraphQL is single endpoint. You understand me now? That is one thing. I'm looking at things that are very specific to the single endpoint. You always hit that single endpoint for GraphQL, but for REST, you have maybe one endpoint for user ID, another endpoint for username, another endpoint for maybe let me say items. So, but in the case of GraphQL, you will see that they just one endpoint that can allow for query, use that endpoint to allow for query and get the information. But all of them, the 2 of them, are executing contracts as it were. So we talk about gRPC. It's HTTP 2, it's streaming, strongly typed contracts, protocol buffers, and stuff like that. But let's move forward. So let's look at REST. So in REST, it has HTTP verbs. Verbs are like what the command with which you manage or you manage a REST API. So get is to read or retrieve resources from an API server. Post is to create. Put is to replace. Patch is to is for a partial update, and delete is to remove. So the URL naming, you can see stuff in users and user ID and stuff like that here. But these are very important point that we should know the verbs in REST API, API. So now let's go to GraphQL is operations. So you can query, read data is query. So the verb here is, when you say query, you want to read, it's like get. When you say mutation, you want to write, you want to create, you want to update, you want to delete. Anything that alters that data is mutation in GraphQL. But anything that just retrieve information is query. Then subscription is real-time data streaming. It's like you subscribe to a queue, and you are getting, real-time information as it comes. You get it on that. So that is real-time data streaming. So and the naming convention, you can see single endpoint, post, GraphQL, feed, username, this type, Pascal keys, this and that. So what it means here is that you don't have like multiple endpoints like we have in REST, but just one point for GraphQL, but you can when you have a single endpoint, your mutation, your query, or your subscription kind of embedded or built into that endpoint. So let's look at gRPC. Call type. So this time around, it doesn't use verb. In REST, it uses the word verb for those actions you can perform. It uses the concept of verb. In the case of GraphQL, it uses the concept of operations you can perform. Then in the case of gRPC, it uses the concept of call types. So one is urinary, so one request, one response. SRV streams, one request, stream of responses. CLI stream of request, one response. BIDI stream, that is bidirectional. You understand me now? So these are the ways you can make calls within the gRPC protocols. Okay, so let's look at the 4 key design principles. Now, the best API is the one you can use without reading the documentation. It's like a tagline there, yeah, and I love that. There are reasons for that. So first thing is that the key number 1 is consistency. There should be a consistent naming convention. For instance, we can have /user /v1 /user name /v2 /username /v2 /id item ID. It should be consistent and predictable URL patterns. So that is one of the keys you have to take note of when you are designing for API. Number 2 is simplicity. Focus on core use cases, intuitive, learnable designs. It shouldn't be complicated. It should be just focus on the use cases. It should be intuitive, that without somebody reading homogeneous your documentation before they can know what you are actually doing, or what they can actually consume, or the structure of your contract. It should be that easy, please. It should be that easy. Security. Then the other key is security, authentication and authorization. So here, every API call must be authenticated, must be authorized, and with scoping, those things are important. Then input validation, rate limiting. How many number of calls can you make per minute or per seconds, so that bots and some other bad actors will not kind of take advantage of our endpoint, API endpoint, of your API endpoint. So let's look at performance. So caching. How do you want to make sure that calls that are made and information that are retrieved are cached in memory or somewhere for the next time, so that every call will not hit that endpoint. So there must be strategy around that. So then pagination, minimize payload. How many data will come to a single page before it kind of split to the next page. So all these things are very, very important in designing your API. So if I can recap again, in the 4 keys in designing API is consistency, simplicity, security, and performance. So let's look at API design processes and life cycle. Identify use case. What problem does this API solve? Then the second thing, you define the scope and the boundary. What is in and out of scope? For instance, if your API is querying, or maybe is fetching, or is updating data in some backend systems, it shouldn't have access to the whole system. There should be scope. There should be what is in the scope and what is outside of it. So then performance requirement, latency, throughput, service level agreements. How long does my business workflow allow for wait? How many wait period, can we accommodate for? So, and what kind of downtime, downtime, yes, downtime you can accommodate for. So these are the things that you have to look at. Then security constraint, like I said, authentication model, are we using JWT? Are you using other application and data sensitivity? How do you ensure that data are not being exposed, sensitive data are not being exposed? So these are the API design principles, API design processes and lifecycle. Then when it comes to the design approach now, we can look at top down. We have 3 approaches: top down, bottom up, and contract first. So in top down, start with the highest level requirement. That shows that when you gather your requirement for this API, you look at the highest level requirement. That is where you start from. But when you are using the design approach of bottom up, you begin with exact data model. So that shows that the data model of the underlying backend systems and stuff like that are what you consider first. Then the other approach is contract first. So you define API contract before coding. That's what exactly is in this. What is the use case? What is the problem that this solve? What do we have in scope? What do we don't have in scope? When you define that, and then you start coding from that perspective, So that is API design approaches. Then when it comes to the life cycle of API, API are designed, they are developed, they are deployed, they are maintained, and they are depreciated. So one thing, each stage requires specific gates: design review, code review, security review, SL definitions, and deprecation notice. For instance, when you design for API, that design should reflect the problem that API is solving, and should reflect the scope of data and the security that is required to keep things clean. Then when it comes to code, when you code it, you have to review the code to ensure that this code, like answers to best practices, this code takes, actually reflect the design patterns and stuff like that. The securities and everything there. So, but one thing is that you have to know that even after you deploy your API, it still needs to be maintained. Like if there is anything that needs to be updated, if we find out that maybe at a particular time you discover that the scope of that API is unrealistic, then you have to refactor and remove. Iterate again. Then deprecation. Deprecation might sound very simple, that okay, we don't use it. No, you have to have a system, a process in place that allows or that help you to deprecate, to sunset unused or retired API. Because if you don't do that, there could be a very vulnerable place for security and compromises. So now let's look at the API protocols. We have HTTP, WebSockets, AMQP, and gRPC. So these are the protocols. Now, when you look at HTTP here protocol, it's mostly used within REST API. So you have client, you have your server, you can see the HTTP request, the method, the header, the body, the URL. These are the components of the HTTP request model. You have the request, you have the method, the header, and the body and the URL. So now, like we said, you can retrieve, you can create, you can update, and you can remove information using these API endpoints. Key principle: stateless. Each request is self-contained. Self-method get should not change state. Yes. So if you issue a get, which is just to retrieve information, it should not make an update. So it should contain itself and be aware of what is required to do. Then idempotent, put, delete, save to retry. So at the end of the day, if that particular update is not complete, then it shouldn't be partially complete. It should be complete and complete. So let's look at this status code. 200 series status code means success. 200 is okay. 300 series, it can be 301, 302. It means redirect. 400 means client error. It could be 401, 402 means client error. But 500 series, they are server errors. So common headers. So when you look at your payload, your HTTP payload, in API environment, you have a content type, you have the cache control, you have the authorization, the whether accept or not, then user agent. These are the things, these are the headers that you can be looking at, you can look out for when you are dealing with HTTP protocol payload. So let's look at WebSocket. Okay. So HTTP pooling versus WebSocket. In the case of HTTP, what happened is that when a client make a request to a server, the server make kind of response, right? So the client will always make a request to say, okay, what do you have, before the server can respond. And if there is no data, there is no new information, there is no new information. But the reality is that the client keep pulling information, whether they are there or not. But in the case of WebSocket, connection is open. So the client just make the initial connection. There's a handshake the first time. So after that is done, the client can just, stay and be waiting for the server to save. So if the server has a new information, it will go directly to serve the client directly. So server push data on his own. So that is how it is. So then the client maybe reply, okay, I got it. But what the point here is that the client doesn't need to constantly making a pull request, asking that, oh, do you have information? Do you have information? In the case of HTTP, that is what happened. But in the case of WebSocket, that is not what happened. What happened is that there's initial handshake and agreement and connection. And after that, the server has the responsibility to serve the client when information is available. Server can push data without client pulling. So in the case, persistent bidirectional connection, server can push data without pulling, and ID for real-time apps, chat, stock and gaming. These are the examples of situations and use cases where WebSocket can be used. Okay, let's look at messaging, and RPC. So for instance, when we look at, if you look at AMQP and gRPC, that is Advanced Messaging Queue Protocol. In the case of AMQP, it means that we have a producer. We have a message broker, we have a consumer. Now, what happened is that a producer produced the messages and publish it to a message broker. In the message broker, you can have something like a queue or topic. So okay, now the consumer will not subscribe to the broker, to the queue, or to the topic, and from there pick information. Now, if you look at how we make orders at McDonald's, it's like we make the order, it gets to the queue, somebody at the back office, kind of prepare it and serve it, and gets to take it back to the queue or the message broker, and then comes to the client or the producer. So that is how Advanced Messaging Queue Protocol works. That is how it works. So one producer, one consumer. That is one-to-one direct. One-to-N fan-out method. So the point I'm trying to make here is that in AMQ, there are messaging patterns. It's not just like, oh, one method fit all. No. We understand the concept that you have a producer, you have a broker, and then you have a consumer. But even at that, there are situations or maybe patterns where you can implement one-to-one, a producer, a consumer. And there are situations whereby you can say one producer, many consumers. That shows that you produce one producer, publish to a queue, and multiple consumers kind of subscribe to that. Then we have end-to-end. That is, we have multiple producers and multiple consumers. So these are the Advanced Messaging Queue Protocol patterns that you can have if you have an application or you're building something that will benefit or that will make use of this protocol. Then I will go to gRPC, client server over HTTP. So client stops, type safety, then protocol buffer HTTP, then server service. So now what happened here is that the protocol buffer essentially binary serialization. Here is HTTP transport multiplex, low latency, type safely, strongly type constrained, streaming servers, client bidirectional. So here this is a very good candidate for streaming services. It's bidirectional. That shows that communication can be initiated both ways, maybe from client or producer, client or server. And is strong. The contract is strongly typed in such a way that there is a structure that it must follow. So if the connection or the payload doesn't follow, that structure, that type, the way it should be, then that particular payload will be dropped. So these are the things. These are the available protocols. These are design principles within API environment or API solutions that you can take advantage of. And what I'm just doing here is to give it some flesh, some understanding for anybody who just want to pick up and learn like I do too. So yeah, so with that, I come to the end of this. And at the end of this, I think I've done some work on system architecture. I talk about a single point of failure, one single server architecture, single point of failure. I talk about redundancy and high availability. Under load balancing, I talk about how load balancers distribute connections across to multiple servers, and how some form of the patterns of how, or let me say, algorithm of load balancing. I talk about reliability and high availability. That is the answer to single server architecture. The API designs, I talk about REST API, I talk about GraphQL, I talk about gRPC and the design principles, of API. Then I look at the protocols like HTTP, HTTPS, or HTTP2, and gRPC. So now this is my understanding. This is how some of the skill set and the skills and learning and expertise I have around system design, and I'm just here to share them with people. Thank you.